everyone. We are the traffic collision avoidance system modeling team for the Lockheed Martin project, and we're going to tell you a little bit about what we got for you guys. So here's a little bit of our background. So we use a models-based systems engineering with SysML diagrams to model all the relevant like TCAS software within Papyrus.
All right, so now talking a bit about the actual background behind TCAS, a bit of our problem scope. The first most important question pertaining to the project is, what is TCAS? TCAS stands for Traffic Collision Avoidance System. So it is a standard that is on all commercial avionics. So all planes have this system as required by the FAA. Essentially, it communicates to the pilot and between other planes the position of other air traffic. And if there is the risk of a midair collision, it reports that to the pilot, tells them to take action. So that's something that Lockheed will be looking at having to redesign in the next coming years here. So our project is to specifically construct a model using model-based systems engineering tools of a TCAS system.
So here we have the block definition diagram. It's the highest overview of what we have in Papyrus. It starts at the C130J node and kind of descends in a decreasing order with everything feeding into each other.
All right, so the internal block diagram is the diagram for the plane. It's kind of closer to like the physical diagrams. It kind of shows data flow, RF flow, voltage flow, whether it's sending discrete values or not. As you can see from this TCAS block, you have the TCAS processor and the antenna. The antenna talks to the processor, giving it RF values, and the processor talks to the navigation block through the ARINC 429 data bus, the audio data bus, and the discrete data, which it is receiving from the navigation block, and it's also receiving voltage. As you can see here with the navigation block, we have 4 new blocks here. We have the autopilot block, we have the ADC block, we have the TCAS block, which we were just looking at, and the GPS block. You can see the data coming out that we were talking about from the audio data, the discrete data, the voltage, and the ARINC 429 that is continuing to go to the next level, which is the plane block. Here's just the intercom block. It simply just hosts the IC/DSU, and it is just receiving audio data. This is the communication systems block, which just hosts the CNMU, and it is just receiving the GPS data from the upper block of the plane. Here's the final and top block, the C130J block, where you can see how everything connects together. You can see how the navigation block, which hosts the TCAS processor, is sending the data into the mission computer, and how that is processing the data so that way the whole plane can understand what is going on and all the data can be transmitted throughout the plane.
This is our requirements table, and as y'all can see in the figure, the rightmost column contains the text with which the system needs to operate within. Middle column is pretty much classified between 2 levels. There's avionics and systems level, and essentially those levels are just there to give us an ease of understanding of what these requirements are gonna operate and interact with. About a quarter of the requirements were specified by our clients, and the rest were just formulated by the team, and these all came from FAA guidelines and other documentation regarding TCAS.
All right, so moving on to the next diagram in our model, we have the use case diagram. The point of the use case diagram is to kind of capture high-level interactions, flow of information between the system internally and all of the external stakeholders and actors, as the model-based systems engineering terminology goes. It also includes a lot of the stakeholders which we identified earlier in the project, so regulatory bodies, maintenance crew, aircraft manufacturers such as Lockheed Martin. You're not really seeing a lot of in-depth detail, and that's what the next diagram, the activity diagram, is really for.
So following up what Connor described about the use case diagrams, the activity diagram is an extension of the use case diagram, specifically the logic interactions as well as the physical interactions between the various components of the system. We're going to start out with the initial node. This signal will be transmitted into the TCAS partition to the airspace monitor, where that signal will reach a conditional diamond, and the condition of, is there a nearby aerial object detected? If so, notify the mission computer. Another conditional diamond is evaluated, the threat level. If there is no immediate threat level, then output the traffic advisory to the heads up display partition containing the digital output messages behavioral block. And from there, the program ends. If there is an immediate threat, the next course of action is reaching the behavioral block for determining evasive action. Then that signal is transmitted to a behavioral block called transmit message to pilot. That signal is transmitted to a fork, what happens at this fork, the signal is basically forked into two parallel signals. So that signal will be transmitted to the pilot's response behavioral block, where it is transmitted to the conditional diamond, and the condition of pilot initiated the recommended evasive action will be evaluated. If no, reiterate the resolution advisory and escalate urgency. And then another conditional diamond will be reached where the question is asked, is the threat resolved? If yes, immediately end the program and continue the monitoring process. If not, loop back around to determine evasive action behavior block. If there is no object detected within the airspace, that signal is bypassed all the way to the mission computer partition to output the message to the pilot via the heads-up display, airspace clear. Here is the overall TCAS algorithm. The process going on, there's the input layer containing the various streams of vessel and airspace data. We reach the conditional diamond, is in nearby aerial object detected. If no, then the process loops back and continues to collect data until this condition is evaluated to some other value otherwise. If there is a nearby object detected, then the entire cascade of operations is initiated and then finally transmitted to the processor, where the processor can finally transmit the message to the pilot, and the pilot can decide whether they want to take action or not. And this is the overall TCAS algorithm used to develop these diagrams.